Hello, everyone. My name is Willem van Hoeven from Carnegie Mellon University, and we're here together with Pascal van Henterijk from Georgia Tech to interview Professor John Hooker from Carnegie Mellon University. John was the recipient of the Association of Constraint Programming Research Excellence Award in 2021, which is the reason why he is invited today to share his thoughts on the past, the present, and the future of constraint programming and beyond. John is a university professor of operations research and the T. Jerome Holleran Professor of Business Ethics and Social Responsibility at Carnegie Mellon University. He's a highly influential member of both the operations research community and the constraint programming community. The works that he has written have been influential for many generations of researchers and practitioners in both these areas. They include constraint programming methodology, operations research methodology, logic-based benders, and so forth. What some people in this audience may not know is that John is also an established researcher in philosophy. He has applied his mathematical tools for logical reasoning to problems in philosophy, but he has also published many works on ethics, including 3 textbooks on business ethics in 2011, 2018, and 2021. So, John, thank you very much for joining us today.
Good, glad to do it.
Great. We've prepared some questions, but we'll have an informal style, I think, in answering these. We'll start from the past, and you joined the constraint programming community back in the day when it was not even called constraint programming. So maybe you can tell us a little bit about what it was like in the early days.
Yeah, so actually, I've had a long-term interest in logic. My first PhD was in philosophy and logic, and this is what attracted me to constraint programming. It seemed to be based to some degree on logic-based methods, and I found that to be very interesting. Also, it was a new direction. I had studied operations research at that point in math programming, and I was looking around for new ideas, and this new CP community was open to new ideas. In fact, I didn't attend the first CP conference. That was the one at Newport, Rhode Island. But I did have a paper in the proceedings, and that was a paper I did on what turned out to be logic-based Benders decomposition, which was one method of combining CP and OR. That was with a student of mine. And I attended the second one that was on Orcas Island in Washington State, US. It was a very interesting meeting. In that same year, I co-organized a meeting that tried to bring together people in this new sort of area of CP. I'm not sure it was called CP then, and people in optimization and operations research. So if you look at some of the names that were at that conference, this was on a mountain in Oregon at Timberline Lodge. It was in fact, we had a freak snowstorm and we all got stranded on the mountain during this meeting, which was a nice place to be stranded. We couldn't get off because of the slick roads. And we had a lot of the people who later became well-known in CP were there. A few were. So yeah, that's one way I got started. It was just the intellectual appeal of the field to me.
And you have a background that uses logical deductions and a very different way of reasoning than traditional operations researchers, which is what attracted you also.
Yeah, the idea of filtering domains is a logical deduction problem. So I thought that was the direction that we should take. Also, prior to that, I became familiar with Robert Jaroslaw, who was an OR person. He was actually at CMU before my time, but I went to a series of lectures that he gave in the late 1980s at Rutgers University. There was an institute there called RutCore, and they had some very interesting workshops. So the very first workshop they had, he gave a series of lectures on logic and integer programming. And I was on the edge of my seat. In fact, he was trained in formal logic. He studied with Anil Narode and wrote a thesis on formal logic. So he applied those ideas to integer programming, and that was right down my alley at the time. I was working on similar ideas, and he was a big inspiration to me. So, and by the way, as a result of that work, he proved a theorem about representability in mixed integer programming, a theorem that characterized which problems can be represented as integer programming problems, mixed integer programming problems, which remains really the only theorem of that kind around. It was a strikingly original idea, and it was due to his background in logic. So that was another inspiration I had back then to get into constraint programming.
So John, if I can interject a little bit here. So I think the first time I met you was in 1990 at a meeting that was organized by Harvey Greenberg and Fred Glover, the intersection of AI and OR. And it was later on a journal issue on the analysis of OR. And so one of the things that struck me at that point was that you were already combining some form of AI and OR as applied to circuits, if I remember correctly, or something like that, and already benders. So how, I think, the way I viewed you at that time was you were this OR professor, actually very well aware of what was going on in AI. So how that came about? Can you explain us how you were like already aware of AI while you were actually, coming from the OR community?
Yeah, actually, that work on circuits was the paper that I published in the first CP proceedings.
I know, I edited that. So
yeah. So how did I become aware of AI? Well, I guess it was Herb Simon. Herb was around when I was around at that day, and we talked about AI and a lot of the issues in AI, particularly the philosophical issues. So, being around Herb, you had to be around what was happening in AI. You had to be aware of that. So I think that's where I got onto the AI field. And, he viewed AI in a different way as it's viewed now. He saw AI as solving unstructured problems. This is why he wrote his code with Alan Newell called a general problem solver. It was what we call Gen AI today, basically. Okay. So we still haven't achieved what he called AI. So the general problem solver would try to take an unstructured problem, like you would give ChatGPT today, and come up with some kind of solution, even though the problem's not well defined. So that was his idea of AI. So I guess that's how I got involved. Also, philosophy of mind is closely connected with issues in AI, very closely connected. And I had a PhD in philosophy, and I had been, read all the literature in philosophy of mind, for a decade or so. So I was very deeply into that sort of thing at the time. So it was just natural for me to jump into the AI issues.
Can you describe, John, what the field looked like in those early days? I've read papers from people from Asia, Europe, and the USA at the time. Was it already a coherent group of researchers? Were they mostly working on individual and separate research topics?
It wasn't a coherent field, no, just some interesting people doing interesting work. So I think you might divide it into the constraint satisfaction group, which were concerned about consistency, art consistency and that sort of thing. And then there's the more algorithmically oriented constraint programming people who were building systems like CHIP. Pascal was involved in that. So I see CP basically as growing out of constraint logic programming due to some work by Bob Kowalski and Kolmar Auer. I actually had some conversations with Kowalski back in the early days, who was one of the originators of logic programming. And he was an inspiration for constraint logic programming. In fact, one of my former PhD students worked with him, Maria Osorio. She actually got a job at Imperial College London through him and was there on the faculty for a while. So so that was going on. It was this work in constraint logic programming that evolved into, I think, constraint programming, because the unification problem in logic programming is a constraint solving problem. And that was generalized to general constraint solving, and that gave rise to CLP. And that eventually became constraint programming. The basic idea being that A problem specification is both declarative and procedural, right? You can do it as a program of steps, you execute, and as a declarative description of the problem to be solved, like we use in OR. So it was a kind of combination of OR and computer science, both declarative and procedural. And I also like that aspect of the field.
Great. One thing that you have been, I think, very well known for is the integration of operations research and constraint programming ideas, or AI in general, perhaps. You wrote a number of textbooks, one of which is called Logic-Based Methods for Optimization, Combining Optimization and Constraint Satisfaction. That was on my bookshelf and on my desk for 4 or 5 years when I was doing my PhD, for example. It was my Bible, so to say, in terms of what to do research on and to be inspired. And with me, I think many others as well. Most recently, you wrote the second edition of Integrated Methods for Optimization. So I think that it's really one of the core research areas over the past decades, I think, for you. It's grown in the whole field with conferences like CPAOR, sub-communities within Informs and AAAI, and of course constraint programming as well. Can you maybe sketch, if you can, the historic overview of how this emerged? Because in the beginning, as you just said, this community was already in existence. I think you were one of the first actually to do research right from the start on these kind of topics. And how did it grow into what it is today?
Yeah, okay. So the combination of the two fields has been growing slowly, I think, over 20, 30 years. So Simtukas and I wrote a solver that we called Simple, S-I-M-P-L. This was back in the 90s, I think. That was something of a precursor to SCIP, S-C-I-P, which integrated constraint and integer programming. And that's what SCIP stands for, constraint and integer programming. So in that system, we tried to integrate the modeling as well as the solution technology. So I think it was proceeding on both of those fronts. So out of the modeling side came things like MiniZinc, I think, that the Australian group put together, which is a very general modeling framework you can use to integrate these approaches, as well as satisfiability algorithms. And then on the other side, we had the algorithmic, which used filtering and constraint propagation, that sort of thing. So it's hard to say, in general, how it all came together, but these ideas, I think, were evolving in tandem, and we tried to put the two together. SCIP doesn't really get into the modeling side of it, which was something of a disappointment, but it's very strong on the algorithmic side, and of course, it's widely used now because it appeals to the mixed integer programming community. Okay, so frankly, the math programming world has been slow to warm up to CP. Okay, it's a very stable research community. You might say conservative. Now, I'm not complaining about the field I'm in it. Operations research, which I consider to be more general than math programming. OR people are open-minded. It's a great field to be in. I'm not complaining about it, but there has been some resistance to accept CP, just because of the way people are trained. In fact, the first paper I did on logic-based benders, which was inspired by combining CP and OR, that paper was rejected. In fact, Herb Simon used to say, if you're not getting rejected, you're not advancing the field. So I try to keep that in mind today when my recent papers get rejected. Yeah, so that paper was rejected, and then I submitted it to OR, or math programming. I forgot. I guess it was math programming, and it was under review for 7 years while they tried to find reasons to reject it, and finally gave in and published it. And while that was going on, I published that book you mentioned, because I got tired of waiting for the journal, to publish this stuff. It was too hard to get past the referees, so I put it into the book. And I've used that strategy since then. If you can't get the community, Herb used to talk to me about this. He says, if community won't accept your ideas, start your own community. Well, I started my own books. Okay, so I use the books as a way to get around the sluggishness of the review community.
Mhm.
Not that there's no purpose for reviews. Reviews are important, but sometimes you have to take an end route around them. Okay.
Can I ask you some question, John? Because so I'm teaching obviously constraint programming at this point in one of the temple of OR here at Georgia Tech. And when the students, the undergraduate students, this obviously start with linear and mixed integer programming, and then they come to constraint programming and they say, wow, this is so cool for modeling. It's so much easier. You don't have to linearize everything, remember how to transform things. So how do you explain the fact that, kind of the mixed, integer programming solvers are not adopting kind of this higher level language and just linearizing everything automatically, some of the things that you have done in some of your papers, actually. So why do you think there is so much resistance in just adopting the modeling language, not even talking about, the computation model?
Yeah, I think it's partly because it's difficult to formulate a research program around modeling. Someone with a background in mathematics doesn't know how to convert that into a research program. So as a result, people don't do research in modeling. It's not, you don't publish in that area. There's relatively few papers published in. So it just has become a topic of conversation and therefore not a area, in which people advance. So I think that's part of it. It's just not a sort of research program people understand. You don't have the background if you're in math.
Yeah.
Now, there's some people who have done, Jaroslav was an exception, having this logical foundation. He knew what it meant to research modeling issues and how to formulate things in a logical way. So he was prepared for that. So I think that is my explanation for it.
Interesting. So let me switch a little bit about benders, because I think one of the things that is part of the substantial contributions that you have made is popularizing benders. I always remember the graph that you showed at some point that the kind of the explosion in the use of benders in the last 10, 15 years or something. And then obviously logic-based benders. So I'm always interested in actually finding out how you get these new ideas. So can you give us a kind of where that came from? Because benders was not very much used. It's a beautiful theory, and then you expanded it. So can you explain, how you put these things together? Why do you actually spend so much time thinking about benders and popularizing, logic-based benders and following up, follow-ups, developments?
Yeah, that I can credit to Bob Jaroslav. He wrote a paper with one of his students way back around 1990 or so on interpreting the dual of a certain type of linear programming problem as a problem in logical inference. So this is a problem that in which the constraints are so-called horn clauses, which is a particular type of logical proposition. And he noticed that the dual problem is essentially a problem in logic. So you can interpret the dual as a logical inference problem. And I thought that was a brilliant idea and a very general one. So then I thought about benders, because in benders, what you do is you look at the subproblem dual. Okay, the dual of the subproblem can be interpreted as a logical inference problem, where the inference method is non-negative linear combination. Okay, you get in that case, it's the traditional LP dual, not the linear programming dual. Well, just generalize this idea of logical inference and allow any kind of logical inference method, and you have a generalized duality. Okay, and in fact, all the optimization duals we talk about, the surrogate dual and so forth, subadditive duals, these are all the same type of dual. I call them inference duals. So apply this inference dual to the subproblem in benders, and you can generate benders cuts based on different methods of logical inference. And every logical inference method gives you a different class of benders cuts. So it makes benders decomposition incredibly more general. Okay, but in fact, you can solve any problem. Classical benders is only good when the subproblem is linear. But now you can use benders for any problem at all, any optimization problem, because you can just apply the appropriate logical inference method to proving optimality. And you have a new benders method. So that's how I got into it. So I was inspired by Robert Jaroslav.
Interesting.
John, going to get back to the comment about getting it's difficult to get into journals, for example, and the reviewers having some issue with these types of research, especially integration of OR techniques and CP. If you look at journals today, like Informed Journal of Computing, but also others, they regularly publish these kind of works now. Do you feel that the field is now much more mature and basically established as a subfield of both CP and operations research, mathematical programming?
Yeah, actually, I lobbied to establish a department in that journal on constraint programming. In fact, I was the first department head for that field. And so, yeah, so that got it started with the journal. That's the reason the journal today is open to papers that bridge those two fields. Yeah. So, and Harvey Greenberg was a major figure. I think he won his award, right? That the first thing, whether it was a very appropriate award, that was for decision diagrams, because Harvey was very open-minded and he was interested in new and up-and-coming ideas. So his influence over the journal, I think he was one of the founders of the journal, was important in establishing the breadth and of the coverage in the journal.
And with that, and with solvers such as Skip, do you feel that the integration of CP and math programming or OR is done?
No.
Are we there yet? Are there still huge challenges, opportunities, obstacles?
We're definitely not there. Skip takes us one step in that direction. The solver I mentioned, Simple, takes other steps, although it's more of a research code. In fact, that was another paper I had problems getting published. It was under review for a long time, and I would send in results where it was beating the heck out of Cplex, and reviewers just wouldn't accept that. They said, "I can't believe you're better than Cplex." Do some more tests, and the more tests we did, the better it got. So they finally relented. But that was that. There was modeling ideas in our solver, but that's not the case in Skip. So I think there's a long way to go, certainly on the modeling side. Now, MiniZinc is attacking that problem, okay? And they work at the level of combining solvers, of integrating solvers as opposed to an integrated single solution method. But I think what we want to work toward is an integrated solution method. And it can be done. So this is the idea I've been working on. It hasn't been accomplished. I don't know where this is going to go, but I think it is one possible goal for the future.
Okay. Glad to hear there's still work to be done.
Certainly, yeah.
Okay. Pascal, are you okay if we move to the next topic?
Yeah, absolutely. I mean,
a topic that also is dear to my heart, decision diagrams. You mentioned it before, John. It's something that you started in this form, at least, back in the mid-2000s, 2005, 2006. Now it's becoming a more established research field with applications beyond CP propagation in operations research, math programming, in AI planning, and different application areas, scheduling, for example. Could you tell us what led you to be interested in decision diagrams as a tool, and what your thought process was in going in this direction, which is really pioneering this whole area?
Now, actually, I got into decision diagrams when I was invited to give a talk at the Technical University of Copenhagen by Henrik Andersen. And he is a well-known figure in decision diagrams. He runs a company where they apply them to product configuration. So this is where I learned about their existence. And he had a student at the time, Tarek Hodzic, who was working with him on decision diagrams. And we got to talking. And I told Tarek, these decision diagrams have potential for optimization and constraint programming, for reasons X, Y, and Z. So shortly after that, I was supposed to give a talk at a workshop somewhere in Europe. I forgot where it was. So I was on the email with Tarek while I was in my hotel. And so we exchanged some emails, and I outlined the ideas for how we might apply decision diagrams to optimization. In fact, I gave a talk on that at this conference, this workshop, just on the fly, because I was working on it. So that's how it got started. So we first applied it to constraint programming. as a method for propagation, an enhanced propagation method. But at the same time, we were looking at relaxed decision diagrams. And we applied the idea to 0-1 programming way back then. That was one of the first two papers. So yeah, that's how it got started. And I think, why did I get into this? Because it's logic based, right? Decision diagrams have a direct connection with George Boole. Okay, so decision diagrams actually come out of logic circuits. Okay.
Randy Bryant.
Oh yeah, absolutely. Yeah. He was one of the figures here. Yeah,
Absolutely.
a colleague of mine here at CMU used to be anyway.
Yeah, so 88 or something. Yeah.
Yeah, so it's a fascinating story, you know.
Even before that, yeah.
Yeah, George Boole was forgotten for almost a century, except a philosopher named Charles Sanders Peirce was familiar with his work, and he had the idea of applying Boolean logic to switching circuits. Okay, that's where Claude Shannon got the idea of modern computing. He was forced to attend a course in philosophy at University of Michigan, and he learned about Peirce and his work in logic circuits, and later wrote a master thesis at MIT on applying Boolean logic to electronic circuits. So about shortly after that, a guy named Lee, I think, came up with the idea of trying to formalize the reasoning that was going on in these logic circuits. And that evolved into a diagrammatic representation of this reasoning process. And those diagrams became BDDs, binary decision diagrams. Yeah. So the BDDs came directly out of Charles Sanders Peirce and Claude Shannon, which came from Boole. So it's a logic-based approach to reasoning for optimization and constraint programming and so forth. So that was one reason it was attractive to me.
And in this area, are there any specific topics that you feel are unexplored and have huge potential?
Well, one is stochastic decision diagrams. Since decision diagrams are closely related to dynamic programming, and most dynamic programming applications are in stochastic dynamic programming. So that suggests we should use decision diagrams in a stochastic mode, and I've done some work on that. So that's, there's actually some parallel work in the AI world on that a little bit that people have done. So yeah, I think that's one direction we can take. So I've been looking at relaxed decision diagrams that are stochastic in nature. The relaxation problem there is much more difficult than it is for deterministic decision diagrams. But there are conditions under which you can relax. So I think that's a totally unexplored area. I think there's even potential to revolutionize the stochastic DP using relaxations from decision diagrams, because relaxation in DP is very important, you know, for look ahead, you know. The cost to go function has to be bounded somehow to get some kind of bound on the optimum. So yeah, that's one area for sure. A more speculative area, I think, for decision diagrams is unordered decision diagrams, something like automata, you know. So we use decision diagrams in layers, and every variable corresponds to a layer. How about a more general structure? There's something like this in AI, you know, recurrent neural networks, okay, have cycles in them as opposed to a directed network. By the way, there's an interesting connection between neural networks and decision diagrams, and that is deep learning. You know, deep means many layers. So it was discovered at some point in the 90s that if you add more layers to the neural network, they work a lot better. And that's because the amount of information you can store in a neural network increases exponentially with the number of layers, because the number of paths in the network is exponential in the number of layers and the depth. This is why decision diagrams work. The number of paths, the number of feasible solutions increases exponentially with the depth of the network. So you have this exponential advantage. Okay, this is why you can represent, you know, many functions polynomially that are exponential in character
Mhm.
using decision diagrams. So there is that connection. Well, why not take the cue from recurrent neural networks, which, by the way, are modeled after the human brain. Apparently, memory circuits in the human brain and language interpretation is based on a recurrent type mechanism in the brain. This is where people got the idea for language models, or large language models, from the human brain. Maybe we can apply this to decision diagrams and see where that goes. I really don't know how to take that forward right now, but it's I think it's worth thinking about.
Yeah, there are some works that train over decision diagrams some probabilistic models where the decision diagram will give you the combinatorial structure within which you can sample in a sense. It's not exactly the same that you just described, but there's definitely work in that space also from the AI point of view. They don't use relaxed decision diagrams, but though, as far as I know.
Uh-huh.
Yeah. Pascal, you want to take it over?
Yeah, so I think John, at this point, I'd like to kind of ask a kind of a meta questions, because when I looked at all the things that you're talking about, I mean, a lot of what you seem to be extremely good at is like you take ideas from different fields and put them together with a very strong focus, obviously, on things that are related to logic. So, but how does that happen? Because you have a number of things that are very different, and then you seem to, somebody tells you about something and you make these connections. So it's not natural for many people to do that. So can you explain a little bit your thought process? How actually this is happening in your brain?
Yeah, actually, I have a sort of another life in which I do cross-cultural anthropology.
Yeah.
So I have read a lot of the literature in cultural anthropology, and I've lived in about 10 countries, and I've tried to learn some languages. So I've had a fascinating experience trying to understand how these other cultures work. And I find that they all have their own logic, so to speak. They have a system or a method that puts things together in a way that lets them deal with life.
Yeah.
So I've got into sort of the mental habit of looking for the inherent logic or pattern in a very different context where the underlying assumptions are very different. So going from one academic field to another is very much like going from one culture to another. You know, we have these academic cultures, right?
Yeah.
And, you know, I tell my students all the time, you know, if you want to publish in field X, you know, the content is not nearly as important as the cultural assumptions that govern how you write your paper, right?
Absolutely.
And what people consider to be an acceptable style and approach and so forth. So, yeah, I think that is that you know, one feeds into the other, right? So I am sort of accustomed to looking at a different field and trying to bridge it with my own cultural background and try to understand, you know, its own logic and so forth. So this cross-cultural, you know, experience. I've taught courses in cross-cultural issues, you know, for 20 years. So that's sort of a natural thing to do academically and research as well. So that's where it comes from.
Interesting. So, and I want to continue that conversation, especially, I mean, these videos are for, you know, young people also to look at the field and understand how, you know, how the field evolved and so on. And one of the things that you alluded to earlier is that sometimes when you change the fields, you know, you change OR or you change computer science, you run into these difficulties in publishing because you're not in the main culture, in a sense. So,
yes,
what is your, you know, and what is your advice to young researchers starting now and saying, wow, I'd like to unify these two fields? And, you know, what would you tell them? Because they're going to run in very similar problems that you had in your careers, and you overcame them, but, you know, not everybody overcomes these kinds of problems, right?
I think it's the nature of the economics of the academic world. You know, I talk to my students about this. I say, you don't want to do what I did. If you want a secure path to the future, it's too risky. You should stick with your field, build a research program in a specialized area and make a name for yourself.
Yeah.
Don't go, dabbling around the different fields like I do, at least until you get tenure. Okay. Yeah, it's a pressure. But I have a checkered background myself, so I didn't have that issue, myself so much as my students do.
Yeah.
I never really had a single forward path I was trying to follow. I was just sort of bouncing around. I'm sort of like that. But yeah, I think we just have to be honest and say it's a risk
Yeah.
if you want to be really innovative. But I think one strategy I suggest is to do both. Do the standard work, get
Yeah.
it published, and in the meantime, on weekends, whatever, do something that really excites you and
Yeah.
keep it going. And then maybe at some point, after tenure, after you have a secure employment, whatever you need, you can put that out there. I don't really have any better advice to give than that.
Oh, but this is good advice. I think, but at the same time, I think it's very rewarding when you look at your career and all the things that you put together, and also all the opportunities you gave to the young generation, right? So you put ideas out there and people take them and put them in directions that sometimes are unexpected, and they branch out to all kinds of different things. So I think that's one of the things that is part of the great work that you have done. So.
Also, industry sometimes gives more opportunity for innovation than academics. Industry was in the CP quite early.
Yeah.
Partly because a number of people in the CP community are good at applications and know how to interact with industry. So, if it works, industry will go with it. It doesn't have to follow their ideology or their customs. So I think that's, if you're working for industry, that might be one way, to try out some new ideas. And certainly we see that in the tech industry now, people trying out all sorts of new ideas.
And that's true. I mean, CP is very, very widely used in industry, although that's a kind of a secret that nobody knows about.
Yeah, I agree.
In manufacturing, and configuration. No, it's like I was on a panel and they were saying, wow, we are using CP all the time. And so it was very, very surprising. So I think I like the connection to industry, and I think at CMU you had also Ignacio Grossman, who was working in chemical engineering, right? You collaborated with him on some of these
projects.
Yeah.
Yes.
So can you tell us a little bit about that? Because that was also one of the ways CP has been used in that community, and had a big impact in other areas like continuous optimization. I mean, global optimization. So can you talk a little bit about your relationship with Ignacio and the way that whole track developed, based on some of the things that you had been doing?
Yeah, I think I mentioned Maria Osorio. She was his student originally, his PhD student. So she started working with me, and so there was sort of back and forth there. And Ignacio got interested in this combination of CP and OR, and he was very early, and he wrote one of the earliest papers on logic-based benders, combining the two. I think it was the year after my book. He wrote a paper. So he had he is deeply connected with industrial application.
Yeah, absolutely.
And so he has had a lot of influence in spreading CP ideas in the industry, for sure.
Yeah.
Yeah, including also Nick Sahinidis, who was at CMU also with the Baron solver, using a lot of CP propagation techniques.
Yeah, he did.
Yeah, so the story I hear is that Nick was somehow convinced to attend a CP meeting at one point, maybe in the early 2000s, and he came back and integrated those ideas into Baron, the solver. So Baron now has essentially constraint propagation in it. It's an important element of the solver. Yeah.
In the interest of time, I have two topics left. I have a topic that's called ethics and constraint programming. And the other one is the future of constraint programming and operators research in the context of the rise of generative AI. Your pick, John.
Well, let me say something about ethics, since that's a big part of what I do. So people often ask me, what does ethics have to do with all this optimization and math and so forth? Well, actually, I'm writing a book now. I'm writing 2 books, but one of them has a chapter with the title Ethics as a Cousin of Mathematics. So I see ethics and mathematics as very closely related. The type of reasoning they use is deductive. Okay. So we live in an age that's very strongly empirical in nature. Empirical science is really the only science we recognize, but everyone forgets about mathematics, which is not empirical at all. It's a deductive science that's extremely useful in applications. Well, this is how one can conceive of ethics. It's deductive science like mathematics. There are theorems and proofs. In fact, Baruch Spinoza, the philosopher, actually wrote a book called Ethics, which was in theorem proof format. It's like a Euclidean mathematics textbook. Okay, so I treat ethics as a theorem proof type of field, and so it's a natural transition, or even if not even a transition really. Just the language is a bit different, notation's a bit different. Okay, and you have ethics. So I think yeah, it's the methodology that's common between ethics and mathematics. So constraint programming, I don't think has any particular relevance to ethics, except that it uses the same methodology. Also, one particular area of ethics is distributive justice. What's the best way to distribute resources to balance fairness and efficiency and so forth. And that's mathematical, both in the historical sense and in the methodological sense. You use mathematics in that area, and there's a whole field called welfare economics that deals with this. Then use mathematical modeling for that. So I'm working very much in that area now. It's not really a constraint programming area, but I'm just struggling with that today. Working with literally today, I'm working on a problem in social choice theory, which is an ethics problem with mathematical modeling involved. Mm-hmm. So that's the ethics thing. AI, yeah. The problem with AI is the hype. It's sort of buried in the hype around it, in my view. I know Willem has a different view on this. Okay. Yeah, so can you get beneath the hype and understand what's really going on in AI? Well, I think AI there's no reason it's not possible, to create AI. Mm-hmm. I have no problem with that. It's the intellectual foundations that I'm interested in. So I think, to me, the most interesting intellectual content in the AI field is cognitive psychology, because AI is really strongly influenced by models of the brain. Alan Newell, who worked with Simon, was very famous in this area. He was the seminal thinker, wrote a book on it. And so I think this is teaching us what it means to think, okay? What self-consciousness is. We've had some really remarkable progress in understanding what self-consciousness is and awareness. And this is very important for ethics, because ethics is all about autonomous choice. And autonomous choice is, in some sense, a self-consciously made choice in which you deduce reasons for your actions and so forth. How does that happen in the brain? Well, we now sort of know, what self-conscious autonomous choice is. It's helped us to understand this, conceptually. Philosophers of mind struggled with this for a long time, but only now, I think, with the help of studying our own brain, are becoming to realize conceptually what autonomy is and self-consciousness. And AI is part of this nexus of inquiry. And this is, I think, to me, the most interesting aspect of AI, is the connection with all these other issues.
Mm-hmm. And so you believe that this issue of, self-consciousness can actually be built in actually AI system? Do you think?
Yes, I think it can, absolutely. In fact, one thesis I make is that autonomous action can be a property of machines no less than people, and will be at some point. So this means that machines will have obligations and rights. It also means that machines, to the extent that they are autonomous, will be ethical, because this is a condition for ethical behavior, is autonomy. Yeah, this comes out of deontological ethics. So there's a whole field here. It's a really interesting area, I think.
Absolutely. And so how do you think, how do you think that's gonna be realized in a sense? What does it take to build a machine like this? How does it take to make it ethical when it's already very difficult for humans to be ethical in many circumstances? So as somebody who works at, at the intersection of AI, OR, and ethics, what's your view and what's your views and recommendations on this? This is very interesting.
Yeah, well, the essence of autonomy is the ability to give a coherent explanation for your actions. Explain why did you do this? This is an old idea. It goes back centuries in philosophy. In a certain, limited domain like manufacturing, we'll have a decision maker on the factory floor that's a machine. That's making decisions about production and when to shut down and so forth. And you ask the machine, well, why did you shut down today? Well, it's because of this and that. Well, why is this important? Well, it's because, once the machine can do this, can carry on a dialogue, at least in a specific domain, as to why the decisions are made, you have a moral agent, as we say in philosophy. You have a moral agent with rights and duties. So we're going to have to accord rights and duties to machines up to a point. To the extent that they can autonomously explain their decisions. Okay.
I would imagine that machines could be much better at this than humans.
Machines are probably going to be easier to teach ethics than humans. It's very hard to teach ethics to humans because humans are not autonomous. People act out of habit, emotion, impulse. We are, this so-called, was it type 1 and type 2 reasoning and so forth, most of the time we do not act deliberately. We act out of habit and conditioning, just the way we are. So it makes it hard for humans to act ethically.
Or also explaining why you acted in a certain way. It's near impossible in these situations.
It's impossible. Yeah, you can't think it through, but machines can think it through, at least in a limited domain, potentially. So I think it actually might be quite pleasant living in a world where we have ethical machines. You can always trust these things that do the right thing.
Or a robotized judging system, like judges that are robots and have clear ethical views.
Judging?
Why not?
Well, that's a different issue. Judging whether an agent is ethical is a very different problem than being ethical as an agent. So I think I wouldn't want to go that far.
All right.
So, John, is this going to be part of your next book, or?
Yeah, it's in there. Yes, yes.
That's going to be fascinating. Yeah. Okay, great. Excellent.
Excellent. Well, thanks very much, John, for joining us and sharing your views on constraint programming and operations research and ethics and much more. Thank you also, Pascal.
No, it's always a pleasure to listen to John. I mean, I remember, several times I visited CMU, and then listening to John is always a pleasure. So always learning many new things and connections. So real pleasure to be here.
Yeah, my pleasure as well. And thank you for the conversation.
Thank you, John.
Great, thanks.
Thank you, Willem.